An integral is often written like this, but is the f of x dx bit just notation? Does it have a meaning on its own? Well, yes. These are known as differential forms, unifying many kinds of integrals you might have come across. Historically, differential forms were just that, the thing you put in the integral. It wasn't until much later it adopted the current definition. We'll visualize this definition in the next video, but for now, I want to talk about why mathematicians cared about differential forms in the first place. In your calculus class, you might have used the u substitution many times, and the usual justification is to go back to how derivatives are taught. Since the derivative of u of x is the limit of the slope delta u over delta x, delta u approximately equals u prime of x dx. By abuse of notation, this is written as du equals u prime of x dx. We can play a similar game for multivariable functions. When you move a small distance of delta x and delta y, the corresponding change in f is, to first order, partial f partial x delta x plus partial f partial y delta y. Again, we replace the deltas by d's by abuse of notation. It's not hard to imagine that this generalizes to a function with however many variables you like. Here comes the question that mathematicians wanted to know. If I have a function f depending on x1 up to xn, then I can find df this way. However, if I'm given a random combination of dx's, is it always possible that there is an f such that df is the expression I am given? The answer is not always, because there are some relations between these coefficients. Since it doesn't matter which order you do partial derivatives, if I write these coefficients as a1 up to an, we have this relation between the partial derivatives of the a's. We can then rewrite it as the difference between the partial derivatives being 0. Of course, there is nothing special about the first two coefficients. Every pair of I and j should work. That means if I have a function f, then the coefficients have to obey these relations. But if the coefficients obey these relations, can we always find the f? That was the question we are asking. It turns out that this is true, with some important caveats. These relations between the partial derivatives are known as integrability conditions at the time, because finding f, given its derivative df, is kind of like integration. It's a bit ironic that integrability conditions involve checking derivatives, but that's how it goes. The story doesn't end here, because rephrasing the original question allows us to generalize. Let's put all these under the integral sign and actually integrate it along a path gamma. Even if you haven't seen path integrals, the important bit of the story is if we can write this in terms of df, then the integral is f of b minus f of a, where a and b are the endpoints of the curve. That means even if I chose a different path, as long as the endpoints are fixed, I should get the same result. This leads to a somewhat different notion of integrability. The integral of the dx's only depends on the boundary. In this case, the boundary of a curve is the endpoints. Again, there are some asterisks to all these, and we'll talk about it later. With this notion of integrability, we can ask if something like this is integrable, where each term has two dx's rather than just one. The only difference is that we are integrating over surfaces instead, but we are still asking the question whether the integral over a surface S and that over the other surface S tilde are the same if they share the same boundary. In this case, the boundary is a curve. The more general integrability conditions are nowadays known as the Poincare lemma. Similar to the previous case where integrability involves checking some derivatives, some differential form omega, which was defined as just some combination of dxi's at the time, is integrable if some combinations of derivatives equal 0. We've suppressed the gory details, and this D is supposed to be schematic at this point. From then on, two different but related developments emerged. One side studied the asterisks I talked about earlier, and the other tried to properly define differential forms. They added to the developments in algebraic topology and differential geometry respectively. Let's talk about each of them briefly, starting with the caveats, because I find this more surprising. Very early on, D'Alembert presented a curious example. Negative y over x squared plus y squared dx plus x over x squared plus y squared dy. If you run through the partial derivatives, let's call them the Poincare conditions, you can check that it is satisfied after some calculations. However, even if the Poincare conditions are fine, when you integrate it along the upper arc of the unit circle, you get the answer pi. But if you integrate along the lower arc, you get negative pi instead. The two integrals are different even though we started and ended at the exact same spots. So this differential form was not integrable after all according to our definitions. This was the caveat I alluded to a minute ago. There is a hole in the Poincare lemma, and in this example, the hole is quite literal. After all, the differential form is not well defined at the origin because of the denominator x squared plus y squared being 0. So the domain of this differential form literally has a hole in it. In general, if the Poincare lemma doesn't hold, it tells us something about the topology of our domain. Investigating the failure of Poincare lemma spurs development of many concepts in algebraic topology. In particular, de Rham cohomology groups measure precisely how this lemma fails and is directly defined by differential forms. So this is one side of the story where differential forms lead to developments in algebraic topology. The other side leads to developments that have many applications in physics. At the turn of the 20th century, the concept of tensors were developed. You might have heard of tensors transform like a tensor, but I really hate this because it's not even true. Tensors, by definition, do not transform, and that's kind of the point. What actually transforms are the tensor components, not tensors themselves. You can see this in just vectors too. In this illustration, the vector points 3 units to the right, 2 units upwards. But this is only true in this coordinate system. If we change the coordinate system, the same vector will be described very differently. The vector hasn't changed, and it literally just stays there, but our descriptions changed. The vector was originally described as 3, 2, but now it is 3.23 minus 1.6. In this case, our descriptions are the components, so components do transform. You can imagine that if I tell you how the coordinate system transforms, in theory, you can work out how components transform. You just might not know exactly how. The scary-looking tensor transformation law spells that out in the general case. But at its core, if you know how coordinates transform, and you know the old components, then not too surprisingly, you know the new components. Tensor is one piece of the puzzle in how the definition of differential forms came about. The other piece of the puzzle was the Jacobian formula. If you want more details, there is a video I made, but essentially it's the U substitution in higher dimensions. Here is the formula for the two-dimensional case. Mathematicians noted that if we ignore the function f and only focus on the dx dy and du dv bit, it looks eerily similar to, but not exactly, the tensor transformation law. So at the time, mathematicians had a vague idea that differential forms can be a tensor, but they are not sure how. It wasn't until much later that a precise definition was nailed down. Because tensors do not transform, they are very useful for physics, including general relativity. Suppose we want to describe a particle and its motion on a sphere. For a curved space, there is no standard way to put a coordinate system on it, and a different coordinate system can be used if that is more convenient. Of course, the particle's position and velocity are actual physical things and shouldn't depend on some artificial choice of coordinates. The idea of general relativity is that to predict a particle's motion, we need to know how the space itself curves. In this case, the way the sphere curves dictates how it moves. Schematically, the curvature tensors dictate how particles move in general relativity. Again, tensors are used because our artificial choice of coordinates shouldn't affect physics. These curvature tensors are in turn defined by more primitive objects known as metric tensors. Yet again, these things are tensors because physics doesn't care about coordinates. However, this step is often computationally troublesome, so troublesome that one of the things during this step, known as Christoffel symbols, are nicknamed Christawful symbols. A slightly different perspective offered by Cartan made this step a lot easier. His idea was to use a system of differential forms to replace the metric tensor, which leads to some other differential forms that are effectively the same as the curvature tensors. Just to give you a glimpse of the efficiency, these are the expressions we had to deal with without Cartan's work. But with Cartan's formalism, we don't have to deal with nearly as many computations. While this equation was originally in the context of differential geometry and general relativity, it also appears in gauge theory if you write it in the language of differential geometry. If we don't go all the way to general gauge theory, differential forms greatly simplify Maxwell's equations. It's not just about simplification, because more importantly, it allows us to add the electromagnetic field to general relativity in this language. So that's why mathematicians and physicists cared about differential forms. Initially, they just wanted to know when integrals only depend on the boundary. But in the process, they discovered that the topology of the domain plays an important role, and that differential forms provide an efficient language to deal with general relativity and many areas of physics. But what about you? Why would you care about differential forms? It might be as simple as unifying things you've seen in vector calculus class. The divergence theorem and Stokes theorem? Well, they are just special cases of the generalized Stokes theorem written in the language of differential forms. You might have heard that if the curl is zero, there is a scalar potential associated with it, and that if the divergence is zero, there is a vector potential associated with it. These are special cases of the Poincare lemma, again written in the language of differential forms. In the following videos, we'll explore them more thoroughly, using an amalgamation of Tristan Needham's book and the 2 blog posts by Joseph Mella and Duart Maya, both of whom kindly answered my questions in email. By the way, I have a second channel where I'll focus more on novel topics, so do subscribe there. As always, thanks to the patrons, and I will see you next time. Bye!